So,
Our next speaker is Professor Radu Miculescu from Transylvania University of Brasova, Romania. So his title of the talk is On the Range of Fractal Interpolation Functions. So I would like to invite Professor. So over to you, Professor.
thank you very much. Here is the outline of my presentation. I'm going to start with some general facts concerning Hutchinson-Barsley fractals. Then we'll talk about the spatial extent of Hutchinson-Barsley fractals. And finally, we will apply our scheme to the particular case of fractal interpolation functions. So let me start with a very brief presentation of Hutchinson-Barsley fractals. As it is well known, the concept of iterated function system is due to Hutchinson, and such a system is actually a pair consisting of a complete metric space, XD, and a finite family of contractions, Fi, from X to X. We are going to denote such a system by S, and let us call it by, for short, IFS. The big idea is the following. If we have such a system S, we can construct a function which is called the fractal operator associated with our system S. This function is defined on the family of all non-empty and compact subsets of X, which is denoted by PCP of X, CP for compact. So our function, which is denoted by F sub S, is defined on PCP of X, and it takes value into PCP of X, and it acts in the following way. The image of some compact subset K of X is exactly the union over I of Fi of K. We should note that this function is well defined because our functions Fi are continuous, and since K is compact, Fi of K is compact, and therefore what we have here is a finite union of compact subsets of X, and therefore it is compact. So Fs is well defined. And the basic result of this theory is due to John Hutchinson. The result states that if we have such an IFS S, then the fractal operator Fs has a unique fixed point, which is denoted by A sub S. What does it mean that AS is a fixed point? It means that AS is the union over I of Fi of AS. In other words, AS is made up by smaller copies at itself. And therefore, we can see that AS is a self-similar set. We denote AS, we call AS the attractor of S, and all the sets that are obtained by this procedure are called Hutchinson-Barsley fractal sets. Now I want to say some words about the proof of this result, because in this way we can see why we call AS to be the attractor of S. First of all, I need to recall the basic definition of the Hausdorff-Pompeiu metric. So this time we look at the family of all non-empty bounded and closed subset of the metric space XD. We denote it by P, B, CL of X. B stands for bounded, CL for closed. And then we look at this function H, which is defined on PBCL of X cross PBCL of X, and it takes value into 0, infinity. And the definition is very well known. The distance between A and B is the maximum between these two quantities, we take the supremum over x in A of the distance from X to B and the other way around. So we take also the supremum over x in B of the distance from from X to A. And it turns out that this is a metric. It is called the Hausdorff metric, but actually it was introduced in a very particular case by Dimitrie Pompeiu, a Romanian mathematician, and this is why I'm going to call it the Hausdorff-Pompeiu metric. Now let me return to the proof of the Hutchinson result. The big idea is the following one. PCP of X with age is a complete metric space, and moreover, the fractal operator is a contraction with respect to age. So this means that we can apply the Banach contraction principle, and then we conclude that the fractal operator is a Picard operator. So it has a unique fixed point, which is denoted by A sub S, and moreover, if we start with some compact subset K of X, and if we construct the sequence given by the composition of the fractal operator with itself n times applied to K, we get a sequence which is converging to AS. So this means that in some way, AS attracts by iteration all the compact subsets of X. And this is why AS is called the attractor of the system. It is also very well known that iterated function systems have application in image compression. And this fact is due to Michael Barsley, and it is very important. Now let me pass to the second part of our presentation. Now our aim is to find a finite family of closed balls such that their union contains a given Hutchinson-Barsley fractal. Let me say some words about the reasons of our work. Actually, I want to say why we need this localization of HB fractals. We have some reasons. First of all, sometimes we are forced to take into account the interaction of the image of such fractal with some other items. And this is the case when iterated function systems are used to produce computer-generated objects. Moreover, this localization represents the first step in the process of discrete approximation of HB fractals. In addition, it is connected with the computation of the Minkowski dimension. And finally, it is involved in numerical fractal analysis. So we have very good reasons to study this problem. And here is the framework of our results. We have an iterated function system S. We denote the Lipschitz constant of Fi by Si. And also, we denote the unique fixed point of Fi by gamma I. And here we have our basic result. It says that if rho I with I in capital I are positive numbers such that they satisfy this relation, then the attractor of the system is inside the union, the finite union of these balls with center in the fixed points of the contractions and with radius rho I. So we need rho I to satisfy this relation. Namely, we want to have rho I to be the same with SI times the maximum of the distances between the fixed points of the contractions plus the maximum of rho j with j different from I. All right, so if rho I satisfy this system, then we get a cover of the attractor with a finite number of closed balls. And now the problem is to solve or to get a solution for this system. And this is what we are going to do now. Let us suppose that our set I is in this way. So it consists of I1, I2 up to IN, and also we can suppose that SI1 is less or equal to SI2, and so on up to SIN. And also let us denote the maximum of the distances between the fixed points by capital M. And this is the big idea. We are looking for rho I such that rho I1 is less or equal to rho I2 less or equal to rho IN. Well, if we have something like this, then we can compute this maximum, and then this system takes the following form, is exactly what we have here, and we can see that here we have a linear system. So it's not a big deal to find rho i's. And here we have the formulas for our rho. So we have rho IN is the constant M times SIN times 1 plus SIN minus 1 over 1 minus SIN minus 1 SIN. And for rho ij, with j different from n, we have a similar formula. Again, we have m, we have sij, and a similar fraction. On the top, we have 1 plus sin. On the bottom, we have the same quantity, 1 minus sin minus 1 times sin. And now let us rewrite this relation with the values of rho I, and we get this result. So AS is a subset of this union of n closed balls. So the number of balls is the same with the number of functions that we have in the system. And we are going to call this union of closed balls to be the covering of our attractor. So we get a cover, but we can do more than this. In order to do this, let me say the following result. Let us suppose that we have an iterated function system S and a natural number M. Then we can construct a new iterated function system, which is denoted by S sub m. We have the same metric space, xd, but this time the functions, the family of functions is the following one. We have fi1 composed with fi2 composed with fim, with a1 up to am in I. So we take all the compositions of m contractions from the initial system. And the key point here is that the attractor of S is the same with the attractor of Sm. So this means that if we want to cover the attractor of S, we can apply our scheme for the system Sm. Let me denote by Cm the corresponding cover for Sm, and I should also emphasize that the Lipschitz constant of this composition is less or equal to the product of the Lipschitz constants of the functions. So it's better to work with the system SM because the Lipschitz constants are smaller, and these Lipschitz constants are involved in the formula of the radius for each this ball. Okay, so now if we apply our result for the system SM, we get a new cover of the attractor of S, which is written here. And we can see that now the number of balls is greater. Now we have the number of balls is the cardinal of I to the power m. So we have a greater number of balls, but if we take the limit when m goes to infinity of the radius, this one goes to 0. This limit is 0. So this means that we can cover the attractor with balls having the radii as small as we want. And the price that we have to pay is that the number of the balls is greater and greater. Now, finally, I want to apply this scheme to the particular case of fractal interpolation functions. So let me recall the basics concerning fractal interpolation functions. The big idea is the following one. We have a data set. So this means that we have a set of points in R2, which are x0, y0, x1, y1, up to xn, yn. Here n is greater or equal to 2, and we suppose that x0 is less than x1, and so on, less than xn. And for each k between 1 and n, we consider decay at random between 0 and 1, and also we consider these quantities. AK and BK that we have here, AK is between 0 and 1, and BK has this formula. We can see that in order to define AK and BK, all we need is the data set. And then we have CK and EK. Now here for CK and EK, we need the data set, and also we need the decays. And also we will need this quantity theta, which is 1 if all the CKs are 0, and otherwise is 1 minus maximum of AK over 2 times the maximum of the absolute values of CK. All right, so if we have this set of data, and if we choose decay between 0 and 1, we construct these quantities, these families of real numbers, and using them, we can consider a particular iterated function system S, which is given in the following way. The metric space is R2 with the distance D given in this way. The distance between U1, V1 and U2, V2 is just the distance between U1 and U2 plus theta times the distance between V1 and V2. And moreover, the functions Fk are given in this way. So Fk of x and y is the vector that has on the first component ak times x plus bk, and on the second component we have ckx plus dky plus ek. All right, so starting with the data set and with the family of real numbers dk between 0 and 1, we are able to construct these iterated function systems. So this means that our functions fk are contractions with respect to d. And here is the basic result of the theory of fractal interpolation functions. This result is due to Michael Barsley. And the result says that there is a unique function f bar from x0 xn into R such that f bar is continuous. The graph of f bar is an HB fractal. More precisely, the graph of f bar is the attractor of our system, and also f bar interpolates the data set. So in other words, f bar of xk is yk for every k. So this is why f bar is called the fractal interpolation function. And now we want to apply our scheme in order to find covers for the attractor of S, which means that we will get covering for the graph of f bar. If we want to apply our scheme, we need to find the fixed point of each fk, and this is an easy computation to see that this is the formula for the fixed point of fk. And also we need to compute the Lipschitz constant of fk. This is not so easy, but is not very difficult to figure out that the Lipschitz constant of fk is the maximum between dk and ak plus theta times the absolute value of ck. So I want to mention here that we have the fixed point and the Lipschitz constant in terms of the data set and in terms of the numbers dk. All right, and also we will need the maximum of the distances between the fixed points of the contractions, which is m. It is described by this long formula. And also we will need these two quantities, capital A and capital B. They have some complicated formulas, but they are very important. All right, so now one more thing. What we need also is to see how does look a ball with respect to our distance d. So if we want to take a look at the ball with center xy and radius r with respect to d, we can see that such a ball has the following form. So this means that the border of the closed ball is a rhombus having these vertices. And what we will need is to note that the biggest second component of a point in this ball is y plus r over theta, and the smallest one is y minus r over theta. All right, so now if we apply our result to this particular case, we will get a cover of the graph of f bar, which is given here by this formula. This is the result that I obtained with my PhD student Bogdana Angelina and with Professor Navasquez. All right, now as a byproduct of this result, we can see that the image of the fractal interpolation function f bar is inside the interval with the endpoints capital A and capital B. So in other words, the graph of f bar is inside x0 xn cross AB. And I should say one more time that A and B can be expressed just in terms of the data set and the scaling factors dk. So this means that we have an estimation for the image of the fractal interpolation function. And also, I should say that we can improve this result by working with the system SM instead of the system S. Let us denote the covering corresponding to the system SM by CM. So this means that if we take M big enough, then we can cover the graph of F bar with rhombi as small as we want. Finally, I want to show an example. We have here a data set consisting of 4 points. We take some values for the scaling factors, D1, D2, D3. And here we have the graphical representations for the covering C1, C2, C3, C4, and C5. You can see that the number of the rhombi is greater and greater. And also, we can compute the bounds, capital A and capital B, for S1, S2 up to S5. You can see that the greater is M, the better is the bound for the image. Okay, that's all. Thank you very much for your attention.
Thank you, Professor. Thank you for this nice presentation. So I would like to request to the audience if they have any question. So if not, I would like to thank Professor again. So thank you, Professor. So we'll start our next talk in 2 to 3 minutes.
Thank you very much. Bye-bye.
Bye.